Thank you all for coming to my talk. It's a bit of a change in topic, so we move into science and hopefully not very hardcore science. So I've tried to make it as well, approachable and easy to understand as possible. As you can hopefully get from the title of my talk, I will try to demonstrate that in many, many cases, when we try to understand why big structures fail, and by big, I'm going to talk about nuclear reactor, massively long oil pipelines, space shuttle, you name it. And normally, if we want to understand the reason, we always come to the conclusion that we have to go really deep in magnification. So for example, we need to look at atoms and things like that at a type of a scale. And that's something we are realizing more and more often nowadays. And it's a bit frustrating for, well, researchers like me because, for example, I can be told, we have a bridge that failed, please tell us why. But the only piece I get is the size of my finger, from that bridge, because that might be the very end of the crack that actually ultimately cause fracture and things like that. So, we're trying to compensate by showing nice pictures in presentation, but often we don't get to see, the real thing. So, as I've just said, big structures can fail. So I'm going to focus a bit on nuclear reactor, which is what I mostly do. We also work with oil pipelines, especially from the North Sea. So this is just a small diagram, and there are many, many, and they all reach, the big oil rigs. And if you could see the way these pipelines are sort of laid at the bottom of the sea, there will be a massive boat that starts connecting the different sort of segments of the pipe and welding them. And then they go gently, to the bottom of the sea until they reach the rig. And these welds are actually quite prone to fracture. I mean, they don't fracture that often, but every now and then there will be one that takes them by surprise. So, they're quite keen on understanding, what's wrong with the welding or what could we do to improve it. The same applies to nuclear power plants, but don't get worried about it. Normally, we know pretty well what can go wrong, and what we do is we just replace it way before we think it's going to fail. And that has been, that conservative approach has been very successful, and there are very, very few incidents to report from the nuclear industry. But of course, for the industry, it's a very expensive approach. So they normally want to know, okay, if you understand why this component is failing, then we can try to use it for longer, but maybe optimizing the conditions so that it will perform better. So, that's how the pipelines are laid. So let's move to the next topic. So fracture is going to be one of the things you're going to hear more often in this talk. And the key thing is that although normally by the time you realize that something has broken, it has manifested microscopically, so it's a big crack or it's a component broken into two pieces and things like that. Normally the mechanisms or the knowledge that you need to understand why it failed, they are quite buried into the atomic microstructure. So that's what more and more often we end up realizing. So I'm showing you one of the components that can give a bit of trouble in the nuclear industry. So that's me, although it doesn't look like, without beard. And behind you have a steam generator, which is a 15-meter tall, 4-meter diameter component in a nuclear reactor, which is filled with thousands of tiny tubes that you cannot see because they are inside. And these tubes, every 2 or 3 years, there will be 20 or 30 that will fail. So they will basically break. They normally wait until there are a few hundred, because there could be 40,000 tubes or something like that. And then they replace the whole thing, and it's incredibly expensive. This is, for example, what happened to this pipeline under the sea that I was mentioning. So that's the line of the weld, and normally hydrogen coming out of the oil, as it passes through the metal, will cause embrittlement, and that pipe will become locally very hard, and a bit of pressure or change in temperature will cause it to fail. So these are the problems that we we have to face, and in a second you're going to see how we try to understand them. Okay, so this is just a tiny crack in one of the small tubes inside that big component. And that crack is so small, you wouldn't be able to pass a hair through it. Okay, so it's an electron microscope image. And now we're sort of slowly moving towards smaller and smaller scale. So talking about scale, I have to mention things like wavelengths and light, so that we put things in context. Okay. So remember, if we want to see something, we need some sort of radiation. For example, if we want to see it visually, like with the naked eye, we need visible light. If we want to see something that is too small, we still need visible light, but we use an optical microscope, right? And for normal microscopy, we move at this range of the sort of radiation spectrum, which is quite narrow here. And light, for example, will have a wavelength, which is the distance between two peaks in a wave. And in the case of visible light, this wavelength is between 400 and 700 nanometer. This is 10 to the minus 7, so it's a 10 millionth of a meter. Okay, that's the separation between two crests in visible light. And with that, unfortunately, it's very powerful, but we can only see things which are about 200 nanometer inside. So 200 nanometer is 300 is a 300th of the diameter of a hair, roughly. Okay, so that was great for biology, medicine. For the last 200 years, we learned a great deal just with visible light and optical microscopy. But when you want to understand why metal or ceramics or harder materials fail, this is not enough, and we need something better. And here I'm sort of moving through the scale so that you get a feeling what we need. So that's again me next to this big component. So 2 meters, 15 meters, right? So we can see if something has gone wrong, but we still don't know why. Then I'm putting just a hair, so you start getting a feeling for the number. So a hair is roughly 30 micron in diameter. 20 if you're blonde, if you want to know about that. And that will be sort of a 10,000th of a meter, right? So for you to start getting a feeling. This is the type of cracks that are going to give trouble in a structure like this. And as you can see, so this will be roughly the size of a hair. And this crack is, as I said before, 100 times or 200 times thinner than a hair, okay? And all the action is not going to happen here because that has already fractured and opened a little bit more. All the action happens there at the crack tip. That's where it's growing. So for that, you need electron microscopy, which is what I'm showing there. With electron microscopy, you can see things which are as small as a 10th millionth of a meter. Okay? So that's 200 nanometer. And the crack tip is going to be even thinner, which is here. Will be something like 10 nanometers. And things will be changing before this crack opens. So the atoms in the structure are going to start moving around. And if you look ahead of this region and you increase the magnification even more, this is, I think, was at quite a 20 million times magnification. Okay, so imagine in the electron microscope we have a knob where we can go higher and higher and higher in magnification. So you need to go to 20 million times to be able to see atoms, right? And this is what we find in any metal. And in our case, we want to see how these atoms move before the crack propagates. Okay? So for you to put this in context, 20 million times with an electron microscope, with an optical microscope, you cannot go above 2,000. Okay? So that's where the two start making a difference. Right? So that's like a bit of a trip from big macro scale things to very small atomic scale things. Right. So these are our tools. That's what we use when we want to look at atoms. Okay? So we have electron microscope. They look like this. They can be quite tall. So this one is 3.5 meters tall. They cost about 2.5 million pounds. And they normally operate in ultra high vacuum because electrons, they cannot travel in air for very long. So they are generated here. You put your sample there, and you have all your detectors here. And we can see things which are as small as 50 picometer. That is 5 to 10 to minus 11 meter. So for you to have an idea, atoms are separated apart by 100 picometer. Okay? So we can see now things which are smaller than one atom. Okay? Then we also have this machine that it looks like a black box, and it's actually a black box because we don't see what is inside. And it's a really interesting one. And what we do here is we prepare pieces of metal which are in the form of a needle. And the needle is very, very thin. So you can see this is one of these needles in this microscope, actually. Because they are so small, we need that microscope to see what goes into this one. So they could be as thick as 100 nanometers. So that's a 200th of a hair, right? And then we give little bits of energy and we evaporate atoms one by one. And there will be a detector that will tell us exactly what atom left the sample, and we can reconstruct it in 3D, right? So we get a 3D picture. So because I'm running out of time, I'm going to the problem. So we have this massive big component in nuclear reactor. After many years of operation, 20 years, the scientists realized that actually they're getting harder than they should. So the metal normally performs well if it's elastic and it doesn't get deformed easily. The crucial component in the nuclear reactor, which is the reactor pressure vessel, was getting harder than it should. And we didn't have a clue why. And these are 500-ton components that are irreplaceable. So when they go wrong, the reactor has to be shut down. Okay? So we didn't know what was happening. And then they decided to ask for help to the electron microscopy community. And we started looking at the metal. And where there should be just a nice uniform structure, we started seeing tiny precipitates. As you can see, this black thing. Okay? And these precipitates shouldn't be there. But how did they appear? So we prepared a tiny needle, as I said before, from a region containing this precipitate. We evaporated all the atoms from this region. And this is how they look. These are all atoms, right? And we know exactly which they are. So they are rich in copper, nickel, and manganese. But these elements shouldn't be there, okay? In the component used in the nuclear reactor. So what we found out is that actually when in the 50s and 60s, the big steel plates were connected or welded to make that 15-meter size component, they were using copper electrodes for the weld. At that time, they didn't know that copper, 20 years later, because of neutron radiation from the reactor, will start moving around, and two atoms of copper are happier together than separate. Okay? So as soon as they meet, they stay together. And after a while, they cluster, and they form, we call them precipitates. Okay? And these precipitates, they're bad news, because when a dislocation passes through there, so when you're trying to bend the material, it stays there. So the material becomes harder. Right? So that's how we understood why these components were giving trouble. And this is how they look in an atomic image. Okay, so I'm finishing quickly. So this part, unfortunately, I will have to skip. Right, and I'm moving to the conclusion. So hopefully, I give you a bit of a feeling that we need to look at really small places to find explanation for big failure. I work with the electron microscopy community and with other similar high-resolution techniques, and this is a very dynamic community. When I started working on this 15 years ago, we could only see things as small as 1 nanometer. Now we can see things as small as 50 picometer, which is almost 20 times better, and this is just 15 years, right? And we are still advancing. So what we can see today would be nothing compared to what you might be able to see, when you if you work in this area, right? And that's a really good way of understanding what's happening, because we're providing with direct observation. So there is very little room for misinterpretation, right? Because we can see the real thing. And many years ago in the 60s, a very famous physicist, Richard Feynman, said there is still plenty of room at the bottom, when he realized how much you can do with atoms, and actually how much space was around atoms. I would like to change this sentence a little bit, and I will probably use it as there is plenty of room for trouble at the bottom. Okay? You need to understand what's moving on. So thank you very much for your attention.